But as we start valence shell electron pair repulsion and all things that come along with it, I'm going to go slow at first, but I'm under the assumption that you've already learned how to do this last year. And I can start to move quicker at a faster rate, because what I want to do is draw as many molecules for you as you can so that you have a real good notebook full of stuff to go and look back on when you're trying to draw them by yourself.
Any senior who took it this year just submitted themselves. I should have taken the you. But you're a good teacher, so it makes up for it. You're welcome.
Did you hear that? Anyway, so before we get into actually drawing the molecules, though, I want to go through the 4 main things that we want to look at. Okay, make sure you have your slides at home, and I'm about to change something on them if you do. The drawings that you're going to draw are called Lewis structures, all right? The Lewis structures are going to be dictated by valence electrons and by the octet rule. So we have a total number of valence electrons in each molecule, and then the octet rule is going to say, all right, now let's make everybody stable. And you're going to make the drawing make that happen. Resonance has a bad definition there. Everybody prepare to write. Resonance are different drawings by moving a pi bond. Resonance, different drawings by moving a pi bond. That's what resonance is. The definition as written on the screen right now can be confused with the word isomer, and we don't want that to happen. So, resonance is multiple ways to draw one structure by only moving a pi bond. And if you haven't watched the hybridization lecture yet, then you might not know what a pi bond is, and I don't feel bad for you.
Period. It's the 1 line or 2 lines?
It's the second and third bond.
Can I have the electronegativity paper? I can't seem to find mine.
Where's the hybridization?
For resonance, it's in your folder. For resonance, you are adding that it's different ways to draw based on moving a pi bond. Formal charge is a specific charge that is assigned to an atom within a molecule based on the way that it's bonding and what its electrons are doing. Formal charge is wanted to be at 0 as often as possible, which will be a big deal today, as you'll see. And then finally, the molecular geometry is the big memorization part. Do you know all of your shapes? Now, I'll tell you right now, the AP exam will 100% ask you VSEPR questions in both the multiple choice and the FRQ. 100%.
How many?
Usually the FRQ that revolves around VSEPR, 6 is the answer to your question. That will not be an entire VSEPR FRQ. You know how they all have lettered parts? Gives you a scenario, and then there's question A, B, C, D, and E, or whatever. All right, one of those will say, okay, well, now you've found the KSP of this or whatever. What would the angle be of that compound after it's formed? In which case, you need to draw the structure, realize that it's trigonal bipyramidal, and then just write down the angled number that they're looking for. All right, you're not getting a 1 because you're going to memorize the angles.
You're going to get 5,000.
So anyway, this is definitely going to be coming back at you, so you want to know this stuff and memorize those geometries. She never looks at me. I know, Diego distracts me too. Now,
I don't distract you, right?
one of the things that is going to be vital for you to understand is what's meant by electron density. So, if I have element X as my central atom, and he's got these things happening to him, can anybody tell me how many areas of electron density you think he has? 5. All right? Because listen, electron density is every different thing that's happening to the central atom with its electrons. Here, I've got 4 single bonds and a lone pair.
So wouldn't that be 10 electrons?
It would. This would be an expanded octet, which we also covered last year.
Yeah.
We're going to cover it again today because we're going to expand octets a lot in here. But yes, I'll explain why when we get to our first problem. But anyway, this would be 5 areas of electron density with 1 lone pair. That's essential because if you look at the way the shapes are described in your table, that's the kind of terminology it uses. All right? 5 areas of electron density, and one of them is a lone pair. Hey, look here. How many areas of electron density do you see now?
5.
Still 5. Very good. All right? Single bond, single bond, single bond, double bond, lone pair. That's how we count them.
What's electron density?
Areas of things happening to the central atom.
Oh! Okay. Just said that.
What was the question?
I mean, that's in the hybridization lecture, but to answer it, that right there is a sigma bond, and that right there is a pi bond. The pi bond is the second and third bond that can form. But that would have to be bonded to something.
So
But
sigma is the first,
sigma's always the initial one.
that's only if it's bonded to something else.
Right, because these are not sigmas, but they can hybridize them.
But
All right, so that's counting electron densities. Okay.
What a sigma is.
Now the hybridization lecture, man, that's on video. That's not today.
Oh, okay.
Now, it says that a Lewis structure should represent the total number of valence electrons. So we'll be counting that up very often. So if I say how many valence electrons does carbon have, you quickly say 4. All right, from group 14, it's got 4. All right. While we're doing the octet rule, it's important to know that everything wants how many valence electrons touching it, except for who?
The first
Hydrogen, who only wants
1.
2 electrons, 1 bond. Hydrogen can make 1 bond, but of course every bond consists of 2 electrons. So while we're drawing our pictures, everybody wants 8, unless we're expanded, except hydrogen, who wants 2. And we're going to be applying all this in a moment. I'm just trying to get your brain going. And then, all right, listen, Dylan, this one's for you. The atoms that are allowed to break the octet rule are atoms that have an energy of 3 or higher. Look at your periodic table. Look at where energy level 3 starts. It's period 3. All of the elements in period 3 have an energy of 3. Do you agree? It's 3s and 3p. All right? Once they have that energy, they have access to all orbitals with that energy. There is another item on the table with energy level 3. Who is it?
3D.
3D. But they're all empty. So if you look at something like sulfur, all right, who's hanging out there in the 3rd energy level, well, he's a 3p element. However, there's 3d orbitals that are out there with him because he has access to everything with an energy of 3. So he's got the ability to put electrons into those empty d orbitals from 3d, which gives him the ability to bond beyond 8. So the only elements that, again, this is review, the only elements that can expand their octet are ones that have energy 3 or higher.
Can it be in the d orbital? Should they have the, like, manganese?
No, because we're not drawing Lewis structures of metals.
Okay.
Oh, so it doesn't even matter.
Right.
So why are they gonna do that though? Is that hybrid?
Let's see.
Okay.
Oh, I was going to change the slide. Ha! You don't do that. Resonance structures. Multiple ways to draw the same molecule by moving a pi bond around. Now, to be a pi bond, that means we're not moving a single bond around. It's either that second line that's moving, or it could be a triple bond that's moving a line around as well to make other doubles or whatever. Resonance structures are going to be multiple ways to draw the same compound, and the reason that they're vital is because oftentimes one resonance structure is better than another, which means if AP asks you to draw the best structure, that means you have to pick the best resonance, and I'm going to show you today how to pick the best resonance. But if you look at nitrate there, ow. If you look at nitrate there, you'll see that all 3 of those are pretty much identical. Do you see how each one has 1 double bonded oxygen? However, all of them have an octet. All right, no matter which atom you pick in any of the pictures, they all have 8 electrons touching them because every line, bonded line, is worth 2. Does anybody not see that? Now, which one of those nitrates is the best? Well, we have to go to the next slide to examine that. If you look on the back of your electronegativity handout from last lecture, you will see a very wordy VSEPR thing that kind of babies you through drawing the molecules that we're about to start drawing. But also on that sheet is an explanation of formal charge, which is going to be absolutely vital for you to understand. It explains to you how to calculate formal charge, y'all. It's simple stuff to do. But what I really need you to understand the most about formal charge is a perfect molecule has all of its atoms at a formal charge of 0. That's the goal, is 0. To find the formal charge of the entire molecule, we will add up all the formal charges of the individuals. All right? We'll be doing that in just a moment with nitrate. So, hey, can you go in reverse and pull up the previous slide, please? Anyway, all right, so let's look at nitrate. I'm going to draw one of those. All right, so you go ahead and draw it with me. All right, there's nitrate. All right, I want to point out that this is essential for ions. All right, if you end up drawing a VSEPR of an ion, it goes in brackets with its charge on the outside because, as you know, nitrate's -1. But that's in the picture. I'm just copying the picture.
Wait, so if there was like a -2?
Be -2, yeah. But if there's no charge, then no brackets.
Should I put my double bond for you here?
Sure. I mean,
I did it at first, but I was just wondering.
well, I mean, I just chose the resonance structure closest to me, is all I did. All right, so how do we find the formal charge of everything in here? Look here, it's super simple. All you're going to do is you're going to subtract the number of valence electrons these atoms have when they're free on the periodic table, minus the number of valence electrons that they actually have control of in the molecule. When you're counting the ones that they have control of in the molecule, you need to realize that all of the lone pairs belong solely to whoever they're to. Like, see those 2 electrons there? Those are oxygens, both of them. They are both bonded to that oxygen. They love him, okay? But you see that pair? That's a shared pair. Oxygen only technically fully possesses one of them. So while you're counting the number of valence electrons that the individual atoms have control of, they have control of everything that's lone on them and half of all of their bonds.
Okay.
So let's do that oxygen then. What is oxygen's valence count on the table?
7.
6 from group 16.
Oh,
How many does he have control of in the picture?
7.
7. 1, 2, 3, 4, 5, 6, and only 1 of those. And what's 6 minus 7?
-1.
It's his formal charge is -1. That was that oxygen right there.
So it would be the other oxygen too.
Hey, right away, here Isaac said, well, we don't even have to think about that one then, right? He's in an identical situation. Please take shortcuts when you can. All right, don't get angry. Hey, but we need to do, this oxygen's different, all right? Oxygen on the table has 6. This oxygen has 1, 2, 3, 4, 5, 6. He's got a charge of 0.
So he's basically, he shouldn't even be there.
No, it's got to be there. It's good. Formal, yeah, he's perfect. That's right. Right, we call it the Cummings oxygen. It's weird.
No, he's too neutral.
All right.
Well,
He's not perfect.
Nitrogen here on the table, has 5. Do you agree? From group 15. How many does he have in the picture? 4. Therefore, his is a positive 1. Hey, what is the overall formal charge if you add up all 4 formal charges? Hey, guess what? It's going to match that.
Brilliant.
Nitrate is going to be -1.
Nitrate.
Well, y'all know what's up.
So here's the question, though. Is one of the other resonance structures
oh no, went away. We're good.
better than this one? And here's what you're going to want to do while you're getting good at this. You're going to draw them all and you're going to add them all up. But can any of you eyeball the other ones? Will there be a difference? There won't, right? All of the nitrogens are identical in all 3 resonance structures. Also, all 3 resonance structures have one oxygen that's double bonded. Therefore, we could run all this again on the other 2, and you're going to get everything's the exact same. Which means in this case, none of the resonance structures are better than another resonance structure. Now, I know you're sitting there thinking, what does it look like when one is? Give me about 45 seconds. I'll show you. But for this one, they're all the same. Now, the way that we think about resonance is if they all are the same, and you're wondering, well, then which one would be the most common? Really, they're kind of an average of each other. We say that they all kind of exist at the exact same time. One note that I did earlier last period that I liked that I added because it's not in your slides, so this is kind of out of order. I'd like you to realize that if you have an atom that has a bond and a lone pair on it, it might have other stuff. I want you to know, I haven't seen AP ask this, but it just seems like good information. I want you to know that this lone pair is closer to the nucleus than the electrons in the shared pair. A lone pair has electrons that are actually closer to the nucleus of that atom it belongs to than the electron that the atom controls in the shared pair. He's going to be slightly further away because of this other dude over here that he's bonded to. The reason it's important that I mention that is because you're going to see that when atoms have lone pairs, it can throw off polarity. Even if it looks like everything else is exactly the same, a lone pair hanging out by himself can make the molecule polar because of what the negative charges are doing with this pair that's closer to the nucleus. I'll spiral back to that idea. Right, I just made up that would be element X. I just don't want to make it fluorine and then you think, oh, well, in fluorine it's closer. No, this is for whatever element. All right, y'all want, and then pass formal charge. Okay, y'all want to do some drawings?
Yeah.
Uno más. Okay, so I'm not. Well, we'd already done that one. Okay. I'm not going to read this chart to you, all right? Most of it should look very familiar to you. The only thing you need to realize is that when you're trying to identify what's what, you're going to look at, for example, for it to be tetrahedral, all right, it's going to be a central atom with 4 regions, all right? All 4 of them must be bonds. So no lone pair. None of the regions are lone pairs. And it becomes tetrahedral with an angle of 109.5, blah, 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 blah. All right? Realize that that very last column is assuming that everything bonded to the central atom is identical to each other. All right? It's written on there. All right? But a lot of people were getting confused by automatically assuming it's polar or nonpolar. This is assuming that everything is the same. Because if one of them is different, what's automatically true? It's automatically polar, all right, if there's a difference. Then you don't have to worry, is it nonpolar, is it polar? If I have a central atom and I have 3 different elements bonded to it, polar. We don't mess with that gray area anymore.
We don't mess with that energy.
Will you not do what you're doing? Thank
You
you.
get it though? You got it.
All right, guys, write this down. Look, I am purposely starting us off with annoying examples. You're going to see that tomorrow we're going to tear through a bunch quickly because those are very common, easier ones. Let's knock out some of these really frustrating ones. All right?
Oxygen plus potential.
Now, we've got, this is not a closed compound.
No!
Oh, it's
Yeah, because only because Dylan said open.
Oh, you ruined it?
Yeah, he ruined it. He said, oh, it's open. Yeah.
I know, but that's ruining it. Okay. In order to draw my compound, what type of electrons do we care about?
Valence.
Valence. Okay. How many valence electrons does oxygen have?
6.
And how many does phosphorus have?
Oh shoot, I got this. Phosphorus has
4.
And how many does nitrogen have?
4.
So my grand total is 16 valence electrons. Does anybody not see how I got some of those values?
No. Well, I know I see it, but no, look, I do.
How do you pick the central atom?
You do the one with the most.
No, it's
See what's on the other side.
It's not do what you want. I like that. It
Whichever
does
one
matter.
You do the most
All
double
right.
bonds.
The
Yeah,
least,
It'll be O.
the least electronegative
Oh,
is the
okay.
item that wants to go in the middle.
I was gonna
Okay,
say
so we're
All right.
with
There are times when that gets broken. All right, you'll see that hydrogen will break that rule. You'll see that sometimes carbon loves being the central atom. All right, but in general, if you're not sure, the least electronegative will be the central atom. So who's my central atom?
phosphorus.
Phosphorus.
If you could be an element, Mr. Cummings, what would you be?
If I could be an elephant,
An element.
the big one, I'd be Dumbo. Okay.
Oh, okay. Good talk, good talk.
So, if you look on, again, the back of your electronegativity sheet, it really breaks down how to do this. All right, so I'll go super slow for the first one. All right, it says that we're then going to bond the leftovers with single bonds. And then my suggestion has always been to make everything happy before seeing if you've drawn the correct number. Remember, 8 is the magic number except for hydrogen. There's no hydrogen here. So I'm going to give everybody an octet. So hooray, everybody now has an octet. Did I draw the correct number? I have way too many. If you remember, the way that we fixed that was to erase 4 dots, add 1 bond. All right, but you want to do it as symmetrically as you can. So I'm going to erase 4 dots. And now I have reduced the number of valence electrons that are drawn, but everyone still has an octet. Everyone is still surrounded by 8, but now I've drawn a grand total of 18, which is still the wrong number, but we're closer to the right number. So what should I do to fix it again?
Oxygen.
Erase 4 dots and add 1 bond.
I like this. Wow.
And what you'll notice now is not only is there an octet everywhere, but we've drawn 16. So it looks like we're done. But now we care about other things. We care about, are there resonance structures? And then we care about which one's best, because there are resonance structures. And we need to figure out where the best formal charges are. So let's take a look at formal charge. All right, let's start with oxygen. Now look, you already have their periodic table values in your notes. So oxygen is going to be 6 minus how many? 6 is 0. Does everybody see how I counted 6? 1, 2, 3, 4. Every line gets half. 5, 6. All right, let's do phosphorus. 5 minus 4 equals a positive 1. Do you see how I got the 4 in the molecule? 1, 2, 3, 4. Half of every line. Nitrogen is going to be 5 minus 1, 2, 3, 4, 5, 6 is a negative charge. Now that looks pretty good. All right? However, since we have our ability to move some bonds around, to move some pi bonds around, we can look at the possibility of resonance. Does anybody see another way to draw him?
Switch around the line.
Put index.
No, that would be him just floating the other direction. That's not.
So like you put the line.
We have to move around a bond.
You get rid of one and put some
Put
dots.
O with P. Like that.
It's hard.
No way.
What about that? Let's see if my VSEPR still works here.
Because you get P dots.
Depends on how much water you drink.
Wait, doesn't O and P mean the number?
Wait, why did you draw them wrong?
That's a urine joke. Okay. What?
Why did you draw them wrong? Just to show
Well, then this is another way to draw it. Hey, look. 2, 4, 6, 8, 10, 12, 14, 16. It's the right number. There's still an octet everywhere. That means we need to investigate its formal charge. This might be a better drawing.
How can it be better for you at 0?
Let's find out. I mean, well, there was 1 at 0, but these two weren't. The overall's at 0. You're right. That's good. But let's see. Oxygen here is going to be 6 minus 7. Do you agree?
Yes.
And phosphorus here is going to be 5 minus 4, yeah?
Yes.
And then nitrogen here is going to be 5 minus 5.
They're the same.
Same.
But they're not.
They're not the same.
Wait, ask. All right, five. Well, I just didn't know what your question was. 1, 2, 3, 4, 5, right? You see where I got all that?
Yeah.
Are we okay?
Yes. I was just saying it
Oh,
wasn't
because we want
different
the
or
one-
the same.
All right, so here's the big AP jump, y'all. This structure is better than the first one. This is the one that they would want you to draw. The question is why? If the overall formal charge is 0 for both of them, then you remember you get that by adding them up. If you add them all up, they're both 0. Why do I like structure 2 better?
Does electronegativity have anything to do with it?
Yes.
So it's because you want the one that has the greater electronegativity negativity to be negative?
In nature, if we have a choice between oxygen being negative or nitrogen being negative, we choose oxygen. He has the higher electronegativity. So even though everything is almost identical, if one of your resonance structures gives the more electronegative element the negative, he'd be better.
He'd be better.
I'd be better.
All of them were at 0.
That's not probably.
That would be the very best. That would be amazing. Yes. I just can't make it happen here.
So you want the one with the most electronegativity to be negative? Or
If you have the option. Now again, guys, I am doing the more annoying ones. Most of them don't do this, but I've got to show you the ones that do.
Are you allowed to get the one clear?
Sorry?
Are you allowed to get phosphorus long clear?
There's no way to do it and have 16. I mean, yes, phosphorus can have lone pairs in nature, all right, but not in this compound. Hey, look, but that's not the only way. There's another structure. Does anybody see another way I could draw this?
Yes.
Yes.
the exact same.
Put 3 on top.
So there's 3 resonance structures.
That last one was sad.
Yeah, that last one's trash.
Hey, but maybe it's not. Let's check formal charge. Maybe the formal charge of...
It's already plus.
It's perfect already.
Here we go. Here we go. This oxygen is 6 minus 1, 2, 3, 4, 5. All right, that it makes him positive. That already looks kind of suspect. All right, phosphorus here is 5 minus 4. Uh-oh, he's positive also. Nitrogen over here is 5 minus 7. He's negative 2.
Oh, that's a 0 charge too, though. But it's still.
But it's awful.
Yeah,
Look,
it's awful.
no one is... Look, we want to maximize 0. So right away, one of those two had to be better because at least they both include a 0. So this one, yeah,
It's
trash.
It was so suspect.
It's so suspect.
So suspect. He didn't even say suspicious.
Why
He
you have
said
your soda,
suspect.
then you have Coke?
That coat's been open there for like
All right, questions on what's written on the board right now?
No, sir.
Okay,
No,
so,
no.
but we're not even, I mean, we're done with that part, but man, there's other stuff we can ask. What shape is he?
Oh, it's
Linear.
a triple one.
It's bent.
So look at the central atom, all right, and we can use any of the resonance structures. How many electron areas, densities does he have?
2.
2. So right away, he's got, hey look, there's only one shape that has 2 electron densities.
Period.
So then what type of shape is he?
Linear.
Linear, and what's his angle?
180.
180, all right? Now look, this says non-polar, but that's false. He's polar,
Yep.
all right? Because remember, that label is only if they're all identical. These are not identical, they're different. So the moment you're dealing with different atoms around the central, then that last column no longer counts. It's automatically polar. It only counts that last deal if the items connected are all the same atom.
So when you look at the shade, you look at the central item.
Central atom only.
Wait, so would O3 be like non-polar?
Why does it have?
Wait, I'm confused.
What?
The number of them here.
Yes. Yes.
So why is it? Okay, but like, I see a couple lone pairs.
Central atom only.
Oh, yeah.
Guys.
So stupid.
Now, okay, we're gonna do another one. We're gonna try to fit 2 more in, but the third one's really quick. Hey, realize that when I say 180 degrees, I gave you a new sheet. Because I don't want you to just say, okay, 180 degrees. The new sheet I gave you today actually shows you where they're measuring that, and it does it for all the angles. So instead of it being just random values, I want you to be able to know where they are in case they ask you to draw it and show it. Here we go.
Are you just picking the elements?
I'm making up compounds. Come on, we're having fun. I was waking up students.
What?
Job well done.
That's how big I am?
Hey, who is that? Sulfate. My first job is to know the number of dots I'm dealing with. So then, right away,
I'm just like,
I
great,
see
I'm
6. Shh. I see 24. And, oh, -2. What is that going to do to my count?
Oh, it's gonna make it
Oh
go
my God, I
bigger.
remember
Make it go bigger.
You're gonna have 32 electrons.
Any questions on my values?
Name said, thank you very much. You
All
always
right,
want
now,
this in the middle.
again, sulfate is super annoying, so don't get frustrated. Bear with yourself. Tomorrow I'm going to make this feel easier.
She's so salty.
Here we go.
No, no.
So wait, where's the part 2 of this lecture? It just ends with, are we learning about your mic drop tomorrow?
Tomorrow we're just continuing. I have 11 examples I want to do. We're on the second one. All right, so I got 10 more examples to do. You see what time it is?
Yeah.
Technically it's 9 after this one.
Oh, let's go with that.
I bond everything to a central atom with single bonds
Yeah.
and then make everybody happy. There's still no hydrogen, so everyone wants 8. All right, so let's get all these terrible dots drawn.
Wasn't there something else you can do instead of dots?
They're all
What?
staring at me. Their eyes. Still looking at me.
Hey, check it out. Shh, shh. We're happy. It's 32. Life is good. All right?
That's not
Again, it looks like we would be done right here,
Sir,
but yes,
how is that 32?
because 6 times 4, the 6 outer 4 is 24, plus 8 is 32.
Okay. Where's the other 4 on the S?
It's 2, 4, 6, 8.
The lines.
Lines
Yeah,
are worth 2.
okay, but I thought you said that means that they share them. The line means they share them.
That's right. But there's 32 total drawn.
Oh, yeah, okay. Thank you, Mr. Cummings.
Let's check formal charge. All of the oxygens are 6 minus 7. Do you agree?
Yeah.
Yeah, I guess.
Sulfur is sitting there at 6 minus 4. Do you agree?
Yeah.
Anybody not see where I got that?
I will. Do you agree?
I guess.
What's the overall formal charge of the molecule?
-2.
Hey, that's exactly what we knew it was going to be,
Oh!
right? Of course it was going to be
Darn
-2.
it.
All right? But the question is there a better one? Are any of them at 0 right now?
No.
No.
If I can make one show up at 0, that would be better. All right?
Why is it better to have one at 0?
Because that's the lowest possible energy. That's what all molecules want to do. That's the whole point that they bond is to become stable. So a formal charge of 0 is perfect.
So when Dylan asks, like if everything is 0, that would be perfect. Does that not happen? in
Yes.
nature?
Yes. No, it does happen.
Bond onto the O.
All right. So here we go. Shh, shh. How else can we draw it? Watch. Draw this with me.
This is called Vespa.
So why?
If you want to, if I do that up here, it becomes a mess. You'll look at the board and you get confused on what you're looking at. She asked if she can draw unbonded lines to represent lone pairs. Yes, you are allowed to do that. I just learned last period that it was a bad idea.
You're right.
'Cause I did it last
I
period.
see how it's
Can I draw a butterfly?
but I don't like
Hey, look what I did. Shh, shh. There is still 32 drawn. There is still a happy octet on all the oxygens. What happened to sulfur?
Sulfur got an extra one.
He expanded his octet. Is sulfur allowed to do that?
No.
No.
Yes, no, he is. Number 3. 3.
He is in energy level 3 or higher, so he's allowed to do it. This is another way to draw sulfate. So let's figure out what the formal charges are here. Now, we already know these oxygens, these three, because they're the same as those, right? So we don't have to run that again, all right? But look at this oxygen. He's sitting there at 6 minus 1, 2, 3, 4, 5, 6. He's got a 0. Look what I introduced, our first formal charge of 0 for sulfate. Sulfur here is now sitting at 6 minus 1, 2, 3, 4, 5. This positive charge. All right, so the overall charge is still the same because we're sitting here at -3 plus 1 is -2. You don't have to worry about that being thrown off. But hey, look, I made it a little bit better.
Can we make it better again?
We can. And that's why sulfate's annoying, because this is still not the best structure.
Wait a minute, so you mean tell me it's got like 6 resonance structures?
6, it does have 6. Watch.
Exactly. Oh, sorry, I'm just good at it. Yes, we're gonna end up just double bonding all of them.
No, we're not.
Oh, well, yeah. Well, I knew that. I didn't know. I know what we're gonna do. I know exactly what we're gonna do.
Now, there's still 32 drawn, which is one of my rules. All of the oxygens have a normal octet, which is one of the rules. Sulfur is happy to expand, so he's good there. Now, we know what one of these oxygens looks like, right?
So there's 2 zeros.
We know what these oxygens look like, right?
Yes.
But look at sulfur. That's a different situation for sulfur. This sulfur is now 6 minus 6.
Giving you the -2 charge.
Still the -2 charge. This is the very best structure for sulfate. Because if you try to fold in another one, you'll see that it starts to take you away from this perfection.
So it's just the best that has the most zeros.
Exactly. She said, so it's just the best because it has the most zeros? Yes. And keep in mind that the items that have the negatives in the case are the items that would want the negatives if you had to choose between oxygen and sulfur. Because oxygen's more electronegative than sulfur. Do not put your stuff away. I'm not done.
Oh, one more.
I will get this last one. And if you're thinking, how are you possibly going to get another one in? Because, guys, most of them are not this involved. Just there's no reason to make tomorrow harder. We're going to make tomorrow easier. But let me show you. Oh, by the way, what shape? What shape? What shape?
Tetrahedral.
Trigon. No. That's linear.
Central atom with 4 areas, so we know that it's a 4. There's other 4s, all right, because there's another slide.
Oh,
all right, I'm sorry.
right.
4 bonded areas, and look, no lone pairs. The sulfur has no lone pairs, therefore it must be tetrahedral with an angle of 109.5.
Was the area the last year when we would like draw the powder?
Yes, we draw that flower.
I remember that.
Yeah.
What shape is it?
Tetrahedral, all right. What's its polarity?
It's
Non-polar. Because look, these are all identical, which by default is a non-polar molecule. It's got polar bonds, right? The bonds can be polar, but the molecule is non-polar. Let me show you one that's way easier so that we can remember that you are better at this than you might suddenly think you are.
yeah. Sorry.
What?
Write this.
Right it.
Oh, hey, I'm sorry. That sulfate needed brackets around him with a -2 to be the perfect answer. All right, just around the entire drawing, Lewis structure. So that's how you would have put that around that final guy. My bad. All right, if the bell rings, I'm going to finish this slow anyway. Oh, I have 7 minutes. I'm good. All right, here we go. Let's start with a valence count. There's 3 of them. Everybody still good?
Yes.
Uh-oh, ruh-roh, what'd that guy go and do?
8.
plus 1.
So it's gonna give you +1, so it's gonna be 8, not 9.
It's going to take away
Take away
an electron. All right? So we've got to get rid of 1 because positives are 1 less electron, right? Hydrogen can never be a central atom. Why?
Can I take?
You can only make 1 bond, so you can't be a central atom. So let's go like this. I made a central atom and I connected everything else with single bonds. I'm then supposed to make everybody happy. Is anybody happy right now?
No.
I am.
All of the hydrogens are.
Look, it's like Santa Claus.
Hydrogen only requires 2. All right. This oxygen, though, what does he need? He needs a lone pair. Now look, I've drawn a total of 8. Everybody's happy, and there is no chance at a resonance structure. There is no other way to draw it. Therefore, there are 0 resonance structures. All right. Now you could still find formal charge if you wanted to, if you were asked to. All right. In which case, the hydrogens would all be 1 minus 1, right? So they'd all be at 0. While the oxygen here would be at 6 minus 1, 2, 3, 4, 5, which of course makes the overall positive.
And the shape is.
What is the shape?
This is the
Trigonal
wrong
planet.
slide. Gappy.
Yeah.
Oh, he didn't tell me this.
I didn't. You're right, but I didn't think about it.
Wait, can it also be angular?
It's bent or angular.
Guys. How many areas of electron density? 1, 2, 3, 4. So it's got to be one of these guys or the tetrahedral. All right. How many of them are lone pairs?
It's trigonal. It's trigonal, but no, yeah, it's trigonal pyramidal.
It's trigonal pyramidal.
Ooh, God.
Yeah, she said that.
I said that.
What's the angle?
Yeah.
What's the
I'm sorry?
What makes it have 4?
Because this was the flower that we used to draw.
Difference.
What's the difference between less
109.
So the question is, why does it say less than 109.5? It's because you don't have to have the 107.8 or whatever it is memorized.
Yeah.
But you can't say it's 109.5.
Well, what's the difference between that and less?
And then he asked, well, why is there a less? So if it asked you, quiet please, about bent, just bent, you could still just say less than 109 and you'd be fine. But if it asked you to compare trigonal pyramidal to bent, then you have to say that bent has an even lower angle than trigonal pyramidal. Does that make sense?
Typo.
Not a typo.
What is the evidence?
It was the less. You see the less than? He said, why is it that? And I said, because it's really 107 point something, and you don't have to memorize that number. You just have to know that it's
Angle is 107.
the actual angle is 107 point something. But AP only wants you to know that it's less than 109.5, which is just a comparison to the tetrahedral, which was 109.5.
Whoa.
Polar or non-polar?
Oh, non-polar. Or polar.
Polar.
It's polar. Hey, look, trigonal pyramidal is polar if all of the guys are the same. Even if they're all the same, it's polar. Who do you think's making it polar?
The oxygen lone pair.
The big flower.
The
That
lone
dude
pair.
right
the oxygen
there.
lone pair.
I told you, the lone pairs can mess with polarity, which is why that last column will be really important for some of you. We're just going to draw more molecules tomorrow. Don't do the VSEPR tonight. I don't want you to get frustrated. You've got time. Look for lecture 2.